who all have, any experience with quantum information, maybe a course or just casual reading? Okay, so great. Well, most of you on square one, so that's perfect. All right. So my talk will be structured into 5 major parts. First will be prerequisites to get everybody up to speed on understanding proof. Then will be operations and gates. Then superposition, entanglement, measurement, and if time permits, we can do Deutsch's problem. Then we'll finally do proof of the no-cloning theorem, and after that we'll do a quantum teleportation demo. To be honest, no-cloning theorem isn't that hard to prove. It's something you do in one beat, but it's just to understand what's going on, you need these 3, and that's why we'll go through all of them. So, starting off with the prerequisites. All right. So now we start by defining the term. Defining the term quantum state. This is a ray in finite dimensional Hilbert space. Now, a ray is just an equivalence class of vectors. That's referred by a non-zero scalar. And a Hilbert space, if anybody, if any of you were there, Professor Marco's talk, is just, we need to specify finite dimensional because Hilbert spaces can be infinite dimensional. It's just a vector space over the complex numbers. You'll be taking it over the complex numbers. Vector space over C. And along with the vector space, it comes packaged with an inner product. And the inner product we'll be working with is a conjugate transpose, and it's called the bra function because the vectors will be working if are called kets. So when we apply the function to a ket, we get a bra ket. Right? That's called Dirac. That's not me. So that's the bra function, just a conjugate transpose. Yeah. So that's defined it. Then we have a qubit. Qubit is a system defined on a 2-dimensional Hilbert space. Whose state, quantum state, is specified by the form where alpha squared so it's just a unit circle around the origin, and here alpha and beta are both complex numbers. Right. So that's how you specify a system with just one qubit. And the 0 and 1 are conventionally defined by 2 by 1 vectors. Right. And together they form the orthonormal basis and orthonormal basis other, and they call it standard basis. It's not unique. We also have other orthonormal bases like the Automat basis, where plus is defined as minus is defined as okay. So that specifies how we describe a system with just one qubit. Now, systems with 2 qubits or multiple qubits, we define via tensor product. Anybody have any experience working with tensor product? All right, great. So, tensor product. If I have, all right, taking the tensor product over them would just be just for 2 qubits, this is how you define the combined state. If I have this in system A and system B, the combined state of system A, B is specified by this 4 by 1 vector. Great. That completes prerequisites. Now we can move on to operations and gates. Now, since we are specifying vectors as 2 by 1 matrices, we can specify an operation via a 2 by 2 matrix. Give me another 2 by 1. But it can't be any 2 by 2 matrices, it has to be a unitary 2 by 2 matrices. The reason for that is forms of the vectors, they act over. If I apply u on psi, or qubit with state psi, I get the same qubit with state phi. And this is a valid state because this we assume to have this constraint, and hence this will have the same constraint. And the way we interpret this is, like I said, the operation u acting on the qubit state psi gives us the qubit state phi. And yeah, let's go into a few examples. Poly state is simple NOT gate, right? And it's specified by 0, 1, 1, 0. And this is how it's written. And then we also have the Hartmann gate, which is converts the standard basis into the Hartmann base. Right. So, and it's specified by. And then finally, a 2-qubit operation is the C0 gate. It's written like this. This Q0 is called the control qubit, Q1 is called the target qubit, and it acts as if Q0 is 1, is in state 1, then it will flip the 0 and 1 for Q1. And that essentially wraps it up for operations qubits, operations in gates, sorry. There are many others. You have the poly X gates, poly Y gates, poly Z gates, 3-qubit gates like the poly gate, but that wouldn't be material for this talk because we just need these three to understand the quantum teleportation demo and the nucleonic theorem gate. So, yep. Great. Before I move on to so this one, does anybody have any questions? Oh yeah.
Can you explain the bracket notation again?
Oh, the bracket notation. So a ket is just a vector in the Hilbert space. This is how it's represented, and it has values as for data. This corresponds to the bra is just the inner product function. So if I take the bra of this, I get alpha star, beta star. This is a 1x2 matrix, a 2x1 matrix, and put together, please give me alpha square plus beta square. So this is the inner product function packaged with the Hilbert space that I'm working.
Okay.
All right. So. All right. Okay. Measurement. So measurement, entanglement, and superposition, and start the problem. So first we do. All right. Now measurement itself has two parts. We have to first set a basis to measure in, and two, find the probability. Now, for our talk, it will just be the standard basis, which is just 0 and 1. And to define the probability, we say that the probability of measuring 0 in the state psi is, we take the bra function specified by the state psi and 0. The norm of it squared. And T1 is the same. Similar. Right. So this is the probability of measure. So if I have a qubit system in state with a qubit with state psi, and I measure it, I measure the state 0 with this probability, and I measure the state 1 with this probability. Now, that being said, we are working purely theoretically, so we're not concerned with how the measurement takes place or how we derive the results. We leave that to the physicists. And whatever interpretation of quantum mechanics you subscribe to, it's just we only care about these probabilities and the result of the state at this point. Also, one thing to note is that after we do a measurement, the state collapses, so we no longer retain the state psi. So if I do a measurement of a qubit with state psi, after this we just say it's at state 0 if it collapsed to state 0, or if it's at 1, then we say it collapsed to state 1. So after this we cannot retain, we cannot get the state back. So that's one. All right. Okay. All right. Is superposition. Yeah, superposition is the easiest to understand. We've already talked about this before from the plus state. It's just many science popularization articles say that in this state is like having 0 and 1 at the same time. It's not entirely inaccurate, but it's not entirely accurate itself. A better way of understanding it was, if I measure this system, I have a half probability of getting 0, and I have a half probability of getting 1. So suppose I take this state and then evaluate the probability. This gives me 1, 0, hoping is squared. So the probability of measuring 0 in this is half. I will repeat that for 1. Probability of measuring 1 is also half. That's how we should interpret this state. It's not like having both 0 and 1 at the same time. So just watch out for that. All right. So superposition was pretty easy. We can now finally go to entanglement. Yes. Very famous. Entanglement. To define entanglement, we got to define separability. We say that a state psi is separable, state psi on system A and B is separable if it can be written as a tensor product of state of two different systems. And this is what we call the separable state psi. If we cannot write the state psi as a tensor product of two different systems, we say that it's entangled. And a very famous example is the EPR pair, also called a Bell state. Let me make this plus 0, 1. Right. So this is famous. EPR stands for Einstein, Podolsky, Rosen. In I think around the 1940s, they wrote a paper on it, and Einstein postulated that the reason this is so controversial is that if I have is a system AB. If I have system A here on Earth, and I send system B to Proxima Centauri, 4 light years away, and I measure system A in the standard basis, and I get 0, it necessitates a system B 4 light years away. Also has to have a state 0. It collapses this state, giving 0 for me and on Earth. 4 light years away gives 0. Einstein said this was the reason quantum mechanics was incomplete, because this action at a distance meant information travel faster than light. But unfortunately for him, and fortunately for us, we didn't have to do a big rewrite of quantum mechanics. This actually is true. And in 2016, I believe they did a test in EU Delft. I believe it was 2 kilometers apart, and this held up. So we do in fact know that this collapse does happen, this action at a distance does in fact take place. So keep this in mind. This will come handy later on. All right. I have time. Great. we'll just quickly do a segue into Deutsch's problem. Deutsch's problem is really interesting because it's a prototypical example of how quantum computers can outperform classical computers in some sense. So I'll just talk about Deutsch's problem. Right. Okay, before I go into this, does anybody have any questions about the three things? Okay, great. All right, so suppose I have a black box F, right? And I know F maps 0 to 1, 0 to 1. And F takes 24 hours to compute. F takes 24 hours to compute. If I have a classical, if F was accepted classical bits, I wanted to know, and F can have 4 different types. Map 0 to 0, 1 to 1, 0 to 1, 1 to 0, 1 to 0, 0 to 0, and 1 to 1. And then these are the 4 different types of functions. These 2 are called balanced functions, these 2 are called constant functions because they map to a constant value and they map to different values. If I have a classical computer, can anybody tell me how long it will take to determine whether it's a constant or a balanced function? Anybody? You have 24 hours to compute just one input. So if I pass 0, it will take 24 hours to get the result. So it will take you 48 hours with the classical computer. 48 hours. Quite simply because I need to test both 0 and 1 to determine if it's constant or if it's balanced. Right. 48 hours. Now Deutsch asks, can we do better with a quantum computer? Is there some inherent property that allows us to outperform classical computer? Yes, there is. Superposition. Right. So if I define an operation on 2 qubits, x and y, such that we solve it in this manner. We define an operation whereas wherein x's value is retained but y's value is flipped if f of x gives 1. And now he asked, what happens if I put a state which is in superposition? So if I put a u of f and say minus state, what do I get? So look at this one. Clever be rewritten as 2 1 f of x. Okay, I think I should f of x was a isolated into an x dependent phase. So okay, maybe it was like k or something like that. But in this, and then he put plus in this. If you expand it in this exact same way, you get this. So he managed to isolate f of 0 and f of 1 in just one input. Sorry. Where is that? If I put 2 qubits, just one input, I can determine f of 0 and f of 1. And if I measure this first qubit in the Harvard basis, I immediately get whether it's constant or balanced. And so this is one way where in 24 hours, I can figure out whether the function's balanced or constant or balanced. And Bernstein-Vazirani proved an even better example where I can find out the value of an unknown bit string using just by testing each of these bits. Sorry, not each of these bits. Testing all of them as superposition. By course, you need that many qubits, and you can find a value of an unknown bit string using just one straight computation. Whereas in a classical computer, you have to test: is this 0? Is this 1? Is this 0? Is this 1? Is this 0? Is this 1? So that's why it gets really difficult for classical computer, but in quantum computer, this is a straight computation. So yeah, that's one example how quantum computers outperform classical computers. All right. Now we go to the proof. Before we do that, just a little bit of background. In 1982, a physicist named Nick Herbert, he wrote a paper called Flash. It's a protocol to do superluminal communication. Essentially, he said that, okay, at this point, no cloning thing wasn't known. He found a way that if you copy qubits, you can achieve faster than light communication. And his supervisor, I don't know his name, but found that, this had to be wrong, but he didn't know what exactly was wrong with it. So he let it be published. The next year, independently, I think DX and Zurich proved the no cloning theorem. Using Pauli basis. My variant and the variant I'll be explaining here isn't as complicated. It's a simple counterexample, but they proved it using Pauli basis, and hence I'm teaching you about it today. But the problem is that if somebody actually does prove cloning, it would require a massive rewrite of quantum mechanics. Like all the axioms need to be shifted or changed. So, don't ever prove cloning. So keep that in mind. So what is the statement of the theorem? Statement of the theorem is the unknown state arbitrary state of an unknown qubit cannot be copied. This is essentially the no cloning theorem. More formally, this is written as there does not exist a unitary operation such that u of psi 0 is equal to psi. This is a formal way of writing it. Does anybody have any suggestion on how to start? Contradiction. Exactly, yeah. You just assume, okay, there is one that does it. Start by assuming. Assume that this is true. Okay? Now, okay, so your psi can be written as Alright, and now using our tensor products as we've done before, alpha beta 1 alpha beta 1 plus beta alpha 0 plus beta squared. And if you write this as a matrix, you get alpha squared, alpha beta, beta alpha, and beta squared. This is what you get if you expand the right hand side. What if I expand via the left hand? So if I expand via the left hand. Can't be equal to this. Unless alpha is 0 and beta is 1, or alpha is 1 and beta is 0, you can't have this. You can't have this equality. And so that's unity. This can't happen. And yeah, that's essentially a simplified variant of the proof that GI can do. Sorry, Dirichlet with Pauli basis, and yeah, that essentially proves our theorem. But there is still hope on the horizon, because although we can't copy qubits, we can definitely teleport their states. We can teleport that information. That's what I'll be showing you fancy folks today. Okay, great. I will just quickly go over it. So, Alice and Bob want to share a qubit, or at least Alice wants to send her qubit to Bob. So, what they do is, Alice has a common party called T, and that third party is non-biased, doesn't do any weird shit to the qubit. Alice will form an entangled pair with T, and T will form an entangled pair with Bob. And the beauty of this is that Q0 and Q1. Q0 is the state you want to send, Q2 is the state you want to receive it. Can be anywhere in the world. One can be in Waterloo, others can be in Tokyo, and this will still work. So the distance is not an issue here. So, and also, sorry, forgot to mention, Alice and Bob have two classical channels that they have, both noise-free and secure. So bits can't be flipped and bits can't be manipulated in these two classical channels, which will come in handy soon. All right. Okay, we have three qubits, as mentioned before. Q0 is the qubit Alice wants to send to Bob. Q1 is what T has, which acts as an intermediary state, and Q2 is what Bob has. So at the end of this, Bob should have Alice's state. And CRX and CRZ are both the classical channels. Now, I want to randomize Alice's qubit so that, like, to prove to you it actually works. So let's. Okay, you guys can tell me when to stop. Now? Stop? Okay, great. Somebody said. Okay, and then, okay, we initialize the Q0 with that particular state. And now we have four important functions. The mathematics of this I can't go into now for lack of time, but they essentially create entanglement between Alice's and the intermediary parties, and the intermediary parties and Bob's. And then Alice sends the measurement of her state to Bob, and then he can show you. Right. So as you can see, the first barrier between the first two barriers is where step 1 happens, step 2, step 3, and then X and Z gates where Bob 5 gets Alice's state. Okay. So set this. Oh, I forgot to. Remember, this is Alice's state, yeah? And let's see if it actually works. Yay, there we go. Okay. This Q2, remember, Q2 represents Bob's qubit. That's at the end of his at the end of the computation. That's his state. And look at Alice's state at the beginning of the computation. Looks oddly similar. It is, because it's the same state. So we successfully teleported a qubit state. Yay! So that concludes my talk essentially. I just wanted to. Any questions? I'm sorry. But yeah, Mark.
You said that information can travel faster than light.
Yeah.
So how does that possible?
Right. Yeah, great question. I don't think Einstein or me knew how that's possible. I'm not entirely sure how this actually happens, but it just does. Right? And it's kind of freaky that it actually does. So it automatically happens over any arbitrary distance. So that's the best answer I can give. It just does. Yeah. Any other question? Yeah.
So do you think Bell? So you know, like the answer to like Bell's paradox, right? Which is like close to this. Do you? So there are like two camps of answers. One is that like there are secret dimensions, and the other is that like measurement is fake.
I definitely prefer
if you had to guess.
Measurement is fake.
Okay, so you would go to the measurement is fake.
Measurement is fake. Yep.
Okay, cool.
Yeah.
Could you go over the math under Deutsch's problem again?
Oh yeah.
Sorry, name it. Like, what is the function d of x supposed to represent?
Oh no, f of x. I'm sorry.
Oh.
F of x, yeah.
Oh, and then
so f of x is just a black box, right? And it just maps this set to this set. And all I want to do is define whether f is a constant function, sorry, a balanced function or a constant function. And for a classical computer, I need to test the value of 0 and the value of 1. But if I use a quantum computer and I define it in this fashion, if I define a unity operation in this fashion, in 24 hours, I could determine whether it's biased or constant.
And what does it mean for two cats to be next to each other? Is that just
Yeah, that's system A and system B. Right. So phi E. Right. So put next to each other, it just means that this is just a contraction I use. It's just a contraction, and it's only used for like 0, 0 states or known states. We usually don't write these for arbitrary states like this.
okay?
So plus and minus, when you put them together, it just means system A, system B having one qubit. Okay. So, and anybody else?